Hi students, we're going to see an example of weak acid being titrated by a strong base, and we're going to see the titration at various points in the graph in various segments and see how that affects the pH. Okay, so here's the very first question. 50 milliliters of 0.100 molarity of acetic acid is titrated with 0.100 molarity of NaOH. Calculate the pH when A is before titration, B is when 45 milliliters of NaOH has been added, C is at equivalence point, and D is when 100 milliliters of NaOH has been added. So whenever you get a titration problem, even before you look at what the question is, if you realize it's a titration problem, there are two things you have to find. The first is you need to identify if the acid and the base, there should be base here, are strong or weak, and then draw a corresponding titration curve. So in this case, we have acetic acid, which is a weak acid, and we have NaOH, which is a strong base. So make that identification first and then draw a rough diagram of how the graph should look like. And then the second point is write a balanced equation for the titration. So even before you start looking at part A, B, and C, do that for any titration question. So for this particular question, NaOH is a strong base, it's a weak acid, and this is the balanced equation. Now the balanced equation is important because over here we see that the ratio between the base and the acid is 1:1, and we are going to make stoichiometric ratios between the base and the acid and use it in calculations. So the places where you're going to have, instead of 1:1 ratio, like you may have 1 acid to 2 base if the acid is diprotic, like H2SO4, or if it is one of the weaker acids. So you may do an example in lab with a diprotic acid where the ratio is going to be 1 for every mole of acid, you have 2 moles of the base. So this is how the diagram is going to be for the titration curve. So I strongly recommend that you draw a titration curve, and as you're asked to solve the question, identify which segment of this curve you're asked to find the pH for. So if you see on this segment, there are 4 different places, A, B, and C, very similar to the previous one we saw for a strong acid titrated with a strong base. Now there are some differences between these two diagrams. One of them is that the pH is much lower for a strong acid, as expected. The pH is higher for a weak acid. One of the other differences you would observe is that as soon as the base is added, the pH starts rising for the weak acid. But for the strong acid, it actually remains pretty low for a while before it starts rising. You're also going to see that the equivalence point is at 7 for a strong acid when it's titrated with a strong base. But for a weak acid, we see that the equivalence point is actually basic. In this case, it's over 8. So that is again a characteristic of when you have a weak acid being titrated versus a strong acid. So when you get this question, you should go ahead and draw this diagram, a rough sketch of the diagram. Okay. So let's go ahead and look at part A, which asked us before the titration happened. So that is at part A, even before any solution was added. So what this question is basically asking is, you have 50 milliliters of 0.100 molarity of acetic acid. The Ka is given to you. What is the pH? You don't have to do anything with NaOH. So this you should be able to recognize is a question that's asking you to find pH of a weak acid. So this is something we have covered in the previous chapter. So this entire slide should be a review for you. So whenever you're asked to find pH of the weak acid, you have to write weak acid plus water and the products. Balance that equation. That should be your first step. And then we make an ice table to find the pH. So let's go ahead and write the general equation for a weak acid plus water and balance it. So we know it's at equilibrium, and that's one of the main reasons we cannot say, for example, if the molarity of this acid is given to us as 0.100 molarity of acetic acid, we cannot say, well, the hydrogen concentration is also 0.1. If this was a strong acid like HCl, we could have said, well, if the molarity of HCl is 0.1, the molarity of hydrogen is also 0.1. So we cannot do that for a weak acid. We have to make an ice table. So when you make an ice table, the only information we have at the beginning is the concentration of the weak acid. We don't have any of the other information. So let's fill this ice table as we have done before. If you do not know, please look at the previous chapter where you can review various examples of weak acids and weak bases that we have done. For change, we are going to put negative X and then positive X on the reactant sides, and then finally at equilibrium we're going to have this. So next we are going to equate it all to our Ka. So our Ka is given to us as 1.8 times 10 raised to negative 5. So we're going to say that's going to equal to our products over our reactants, and then go ahead and solve for X. So the X in this case, we solved it as 1.34 times 10 raised to negative 3, and X is hydronium ion, which is hydrogen, concentration of hydrogen. So if you have the hydrogen's concentration, we can do negative log of that to get the pH, which we got as 2.87. So let's go on to the next section. So this should be a review for all of you. Now, before we go to part B and C, just let's look at the diagram. So in part B, 45 milliliters of NaOH is added, and in part C is at equivalence point, right? So can you find the volume of sodium hydroxide at equivalence? So the answer is yes, we can, because we have been given the volume and the molarity. So both of this information for the acid is given to us. At equivalence point, the moles of the acid is equal to the moles of the base. For the base, we are given the molarity. And we do know that the molar ratio between the acid and the base is 1 to 1. So this is the equation that we have. So we can go ahead and find the moles of the acid, where we multiply the volume of the acid by the molarity to get 0.0005 moles of acid, and that is the moles of the base also in this case, because as we said, it's a 1 to 1 molar ratio. And then we can find the volume of it by dividing the moles by molarity to get 50 milliliters as the volume. So what we see in part B is that 45 milliliters is added, and in part C, it's at equivalence point. So at part C, 50 milliliters of our base was added, and in part B, we're at 45 milliliters, so that means we're still somewhere over here. So one of the things you have to notice is if we are over here, we're still in the acidic part. Anything below 7 is acidic, which means we have excess of acid over here, not excess of base. At this point, when it's 50 milliliters, the base and the acid are at the same amount. So we can say the base neutralized the acid. We no longer have any acid at this point. And at this point, we have more base than the acid. So with this information, let's go ahead and do part B. So in part B, we're told that we have 45 milliliters of sodium hydroxide. So what this means is we are still at a part where we have more acid than the base. So let's go ahead and make an ice table. But what is special about this ice table is we are going to use moles and not molarity. And we will go ahead and talk about why we're going to do that. So first, let's go ahead and find the moles of our acid. So we have 50 milliliters of 0.1 molarity. So that's going to be 5.00 times 10 raised to negative 3 moles of our acid. And for the base, we have 45 milliliters at 0.100 molarity. So that gives us 4.5 times 10 raised to negative 3 molarity. So now let's write our equation. Acetic acid plus sodium hydroxide gives us acetate plus water. Now everything in this table is going to be filled in moles. The reason is because the volume is changing. We had 50 milliliters and we're adding 45 milliliters to it. And when we finally do the Ka, we will be using molarity and not mole. So at that time, we'll be adding both the volumes to get the right molarity. But as of now, when we are doing the ice table, we can use moles because that is easier. Otherwise, you may have to divide it by the volume over here So we can go ahead and use the moles for now. So we know we have 5 times 10 to negative 3 moles of our acid. That's what we are beginning with. Initially, we don't have any base added, so everything is 0. Then we are adding 4.50 times 10 raised to negative 3 moles of our base. Now look at this number, 4.5 times 10 to negative 3 and 5 times 10 to negative 3. Now 4.5 times 10 to negative 3 is smaller. So what that means is the base is going to neutralize the acid, but it's not going to neutralize all of the acid. It would have done that if we all had, 5.00 times 10 raised to negative 3 moles, but we don't have that much moles. So after it neutralizes all the acid, we're still left with an amount of acid. We're still left with 0.5 times 10 raised to negative 3 moles of the acid. And as you know, water, because it's a liquid, a pure substance, it's not going to have anything on the ice table, and the acetate ion is going to be 4.5 times 10 to negative 3. Now with this information, what can we do? We can go ahead and put this in the Ka. So Ka is equal to of acetic acid. But before we put it into the Ka equation, we need to convert these moles to molarity. And how do we do that? If you divide the moles by the total volume, you're going to get the molarity. So the total volume is going to be 50 milliliters divided by 45 milliliters. 50 milliliters and you add 45 milliliters to it, so it's 95 milliliters. So if we do that, we are going to get the molarity of acetic acid as 0.0053 molarity, of acetate ion as 0.0474 molarity. And if we put it in our Ka equation, we are going to end up having our H as 2 times 10 to negative 6 molarity, and solving for pH, we are going to get 5.70. So this could also have been solved using the Henderson-Hasselbalch equation. So there may be multiple ways of solving the questions. I'm solving all of them using the ICE table so that there is a single way to do all these questions. But you may see in your textbook different ways of solving the question. So let's go ahead to the third point, which is at equivalence point. Now we already talked about at equivalence point, the moles of the acid and the moles of the base are same. That means we're not really going to have any acid or any base at equivalence point when a weak acid is being titrated by a base. We also realized that it took 50 milliliters of 0.1 molarity of our base to titrate 50 milliliters of 0.1 molarity of acetic acid. Let's go ahead and draw the ICE table so that you can see that. So here's the balanced equation, and when you draw the ICE table, we can say the amount of moles of our acid is 0.005 molarity. The amount of our base is also 0.005 molarity. So we subtract that, we get 0, 0. All that we are left with is acetate in water. So at equivalence point, we just have the conjugate base, and this conjugate base is 0.005 moles. We can convert it to molarity. So if we convert it to molarity, it's going to be 0.005 moles divided by, we have 50 milliliters and 50 milliliters of NaOH. So it's 100 liters, so we get 0.05 molarity. So what we have to realize is when a weak acid is titrated with a strong base and it's at equivalence point, we end up having an equation where it is just the conjugate base plus water, which gives us the acid and the NaOH. So that is going to be the equation that we are going to use to find the pH, because the only ion that's present at equivalence point is going to be the acetate ion. Now, one of the other things you have to realize is since we have the conjugate base, we are going to need Kb. So if it's conjugate base plus water, it's Kb. If it's an acid plus water, we need Ka. So base plus water should be needing Kb. Now, how do we find Kb for acetate? For acetic acid, we know the Ka is this. So for acetate ion, the Kb can be found by dividing 10 times 1.0 times 10 raised to negative 14 by this number, because Ka times Kb is equal to 1.0 times 10 raised to negative 14. So using that formula, you will be able to find the Kb. So let's go ahead and write the ice table for acetate plus water and solve it. So initially we have 0.05 molarity and we have nothing besides that. So we go ahead and do negative x, positive x for the products, and we have 0.05 minus x, x, and x at after the addition. So with that information, let's put them in KB and solve it out. So at this particular case, we are going to solve for x, and what is x going to be? X is going to be OH. And if you get OH, we can find POH, and from POH we can find the pH. So in this case, we end up finding that our OH is 5.3 times 10 raised to negative 6 molarity, and we can find POH from that is 5.28, and pH is 8.72. So now let's go ahead and look at the so this is also one of the important points. The pH is 7, is above 7. It's 8.78 as expected for salt of a weak acid and a strong base. So if you remember from previous chapters, we were talking about the conjugate base of a weak acid. How does it affect the solution? How does it affect the acidity or basicity of a solution? And we had talked about how if you have a conjugate base of a weak acid, it's going to increase the pH. And we see that in this question. So now let's look at the very last part, which is when 100 milliliters of NaOH has been added. Now we know that anything above 50 milliliters, which is the equivalence point, is going to be in this part, which is the D stretch. And when 100 milliliters is added, it is also over here. So we should expect to have a pH that's very basic. So what is happening when you are adding 100 milliliters of NaOH? We already know that at this point, all the acid was neutralized by the base. So we no longer have any acid left. So at this point, we should just have excess of base. Okay? So let's go ahead and write the acid-base equation, and let's write what we have so far. So we have 0.005 molarity of moles of our acid, and for OH we have 0 initially, but then we end up having 100 milliliters of OH, so converting it to moles is 0.01 moles. So if you subtract 0.01 moles from 0.005, we cannot do that because 0.01 is a bigger number. So that means we definitely have 0, but the OH, if you subtract 0.005 from 0.01, we end up having 0.005 moles of hydroxide left. So that means we have more hydroxide left. So in this, we can go ahead and look at the leftover base or the hydroxide and calculate the pH based on that. So we take the moles of our hydroxide divided by the total volume, which was 50 milliliters of the initial acetic acid added with 100 milliliters of the base. So once we have the molarity, we can go ahead and find the POH and then the pH, which is going to be 12.52. So students, with this, we have looked at the various parts of this graph where a weak acid was titrated by a strong base. And this is a very nifty little equation which can help you figure out how to do these kind of problems.